In this lesson video, we'll be looking at Chemistry 1502. The topic for today is nucleophilic substitution reaction. We will be looking at the easiest way to identify SN1 and SN2 reaction, looking at the properties of the reaction that you are given. Let us start. This lesson is specifically recorded for my students which they find it difficult to identify SN1 or SN2 reaction when you are given a reaction without stating whether it is SN1 or SN2. So this approach, it requires a deep analysis. We are going to analyze each and every property that we can possibly see from the given reaction. So throughout the examples that we'll be looking at for this lesson, we will be using the very same procedures. So let us look at those steps, the analysis. Let's say step number 1. We look at the substrate. By now you should be done with the introduction of SN1 and SN2. Because in this lesson we are not going to be looking at the basics, but we'll be looking at how to identify SN1 and SN2. So the first thing that we should look at is the substrate, and by now you should know what is a substrate. So you have to remember that the structure of the substrate is very important consideration in determining if a reaction occurs by an SN1 or SN2 mechanism. So the question should be, what is the structure of the substrate? And you should remember the trend of SN1. Remember the trend of SN1. It trends like this. We have a tertiary alkyl halide, and we have a secondary alkyl halide, we have a primary alkyl halide, and then we have our methyl halides. So the most stable alkyl halide is a tertiary alkyl halide followed by a secondary alkyl halide, and we have a primary, and the least stable is the methyl halide. The methyl halide. And then in SN2 we have a reverse, which we know very well that methyl halides are very much stable, and then followed by a primary alkyl halide, and we have secondary alkyl halide, and lastly we have a tertiary alkyl halides. So that is why I said it's very important for you to watch the lessons based on SN1 and SN2 nucleophilic substitution reaction, so that you can know what is a tertiary, secondary, primary, and methyl halides. So remember this trend. So under step number 1, if your substrate is a tertiary alkyl halide, you should know that definitely sure you are going to have SN1 nucleophilic substitution reaction, and we are 100% sure that it will not undergo SN2. So you should rule out SN2, and then SN1 will be favored. If your substrate is secondary, you should know that the possibilities are, let me actually use this to scratch out SN2. So the possibilities are, let me just remove this. So we are comparing SN1 and SN2 nucleophilic substitution reaction. So if we have a secondary substrate, you should know that it does not favor SN1, but it is possible. And it does not also favor SN2, but it is also possible. So there is possibility that it might go SN1 or SN2. So you should look at other factors. You should look at other properties. Remember that for tertiary, SN1 will be favored, SN2 will not be favored. Looking at primary substrate, we are comparing SN1 and SN2. We know that SN1 will not be favored. There's no possibility that SN1 might be favored. And then we have SN2. And then if we have a methyl, SN1 against SN2, we know that definitely sure SN2 will be favored, then SN1 will not. So this analysis is based on substrate. You should know that for tertiary, SN1 will be favored, SN2 will not be favored. Secondary, either way, either one of these can be favored, depending on the other factors that we'll be looking at, or let me say properties of the reaction that we'll be looking at. For primary, we know very well that SN1 will not be favored. We have SN2. Methyl, we have SN2. SN1 will not be favored. That is step number 1, based on the substrate. Let us go to step number 2. We look at the nature of the nucleophile. Step number 1, we look at the nature of the substrate. Step number 2, we look at the nature of the nucleophile. Now the question should be, is the nucleophile strong or weak, or we can say good or bad? Now we know that for SN2, it favors strong, or we can say good nucleophile. And then for SN1, it favors weak, or we can say bad nucleophile. So if you cannot identify the nature of the substrate, or let's say we have a secondary substrate, then you go ahead and look for the nature of the nucleophile. So it is very important for you to know the types of nucleophiles we have under the strong and weak. The previous lesson videos we did discuss those. Now under the nature of the nucleophile, the question would be, what makes a strong nucleophile? So when you talk about a strong nucleophile, this is what you should consider. Let's say maybe you come across a nucleophile that you've never came across before while you are studying this chapter. A negative charge. So whenever you have a nucleophile that has a negative charge, you should know that we are dealing with a strong nucleophile. We can say that a negatively charged species is a better nucleophile than a similar uncharged species. In particular, a base is stronger nucleophile than its conjugate acid. What is the meaning of that? Let's say we have H2O as our acid. We know that this is an ampholyte, but after donating a pair of, actually a donor, after donating hydrogen donor, we know that it will become OH minus. In this case, this is an acid, and then this is a conjugate base. And you should know that this is a strong nucleophile, this is a weak acid. So if you can be able to identify all the weak acids and the strong acids, you should be able to know whether the conjugate base of each and every acid that you're dealing with is a strong or a weak nucleophile. So if we are to compare nucleophiles which has a negative charge and those that are neutral, we should know that the negatively charged nucleophiles are strong. Another property we should check is the electronegativity. A decrease in electronegativity is an increase in the strength of the nucleophilicity. So looking at this, we can see that carbon is less electronegative compared to nitrogen. Therefore, we can say this is a better nucleophile compared to this one. And we can further say we can continue. We put fluorine ion, right ion. this is also stable compared to H3N, and then we have H2O, then we have HF. If you can look at the electronegativity, you will see that the trend is like this. So far we've looked at the strong nucleophiles. Let us look at the weak nucleophiles. So any neutral nucleophile, let me say any nucleophile with a neutral charge, you should know that it falls under weak nucleophile. And we have also the steric hindrance. You should know that a bulky nucleophile will always slow down the reaction. We will discuss this in detail when we look at the examples. Let us look at the nature of the living group. That is step number 3. You should make sure that you compile notes as we look at the steps. Look at the living group. For the living group, SN1 and SN2, they both favor a good, or they need a good living group. So this step, we don't really need to analyze whether it will undergo SN1 or SN2. As long as you have a good living group, then we should have these reactions. Let us look at the number of good living groups. We have Cl minus, we have Br minus, we have I minus. These are one of the common good living groups. We also have sulfonate, sulfate, phosphate. We also have those neutral molecules, which is H2O, alcohols, amines, and phosphines. And there are those molecules which will never ever be living groups, like the hydroxide. This cannot be a living group. The alkoxide, it can be CH3, CH2O minus. Cannot be a living group. We have the amide. They also cannot be living groups. Let's go to step number 4. Step number 4, we look at the nature of the solvent. Solvent is one of the important things that we should consider when we decide whether it is SN1 or SN2 nucleophilic substitution reaction. You should know that solvent does play a role in determining whether the reaction goes by a SN1 or SN2 mechanism. It is not very much a major role, because sometimes you see that reactions do not indicate the solvent, but should it happen that we see an indication of a solvent, it will actually assure us whether we are dealing with SN1 or SN2 nucleophilic substitution reaction, depending on the nature of the substrate and the nucleophile. So you should know that polar protic solvent, we can say protic solvents, are good for SN1. For protic solvents, we are talking about those solvents which have acidic hydrogens, one of the properties. Then they are very strong solvating power. The examples might be water, or examples are water or alcohols. And then we have aprotic, polar aprotic solvents. they normally don't have acidic hydrogens. Let me actually do this. They also have a good solvating power, but they are not as strong as the protic solvents. They are very good for SN2. Examples are acetone, acetonitrile, we have the crown ethers, we have the dimethyl formaldehyde. The name is actually complicated. It's dimethyl formamide. You will have to forgive me for that pronunciation. So this is step number 4 that we should also consider when we are dealing with identifying whether it is SN1 or SN2. Let us look at the last step, which is step number 5. Step number 5, we actually have to put everything together and decide whether it is SN1 or SN2. Now remember that you have to consider all the analysis, and also remember that the nature of the nucleophile and the structure of the substrate are most important. Another thing that you should look at is the nature of the living group, which is not very much important because we have living groups which they accommodate SN1 and SN2. Then another thing that you should check is the solvent, which is not a very much major factor, but it is very good when you have to identify the polar protic, polar aprotic, so that you can decide whether we have SN1 or SN2 nucleophilic substitution reaction. Let us look at the first example. So it goes like this. All the reactants, this will be our substrate, this is the substrate, and then this will be our nucleophile, and then on top of the arrow, that is our solvent. So sometimes you might see a nucleophile being placed here and then a solvent being placed here. But in this case, I decided to put the nucleophile on the reactant side. We are not going to be looking at the mechanism, but I just want us to identify whether it will be SN1 or SN2. So let us go ahead and apply our analysis. Remember, the first step is to look at the substrate. Let us look at the substrate. We can see that the living group, it's attached to the carbon, which is attached to 2 other carbons. Then it makes this a secondary alkyl halide. So we are done with the first step. Second step, we look at the nucleophile. Remember that the nucleophile, for it to be a strong nucleophile, it must have a negative charge. In this case, you can see that we have a neutral nucleophile, so it makes it a weak nucleophile. Looking at the solvent, we can see this is a polar protic. So what you can do now, you can simply put a table to say we have polar protic solvents against polar aprotic solvents, and then remember this is SN1 and then this is SN2. Under SN1 you can put the first example of polar protic, it's CH3OH. So we can see that secondary alkyl halide with a weak nucleophile. With these two properties, we can conclude the type of nucleophilic substitution reaction this would be. And then we also have a polar protic. then this will be SN1. Then once you can identify the type of nucleophilic substitution reaction this will be, it will be very simple for you to actually write down the mechanism, because you know that we are not going to be having a one configuration, but we are going to have a mixture, and also the way it will attack the electrophile and the way the nucleophile will actually leave the substrate, including the rate limiting step in SN1. So we have applied the analysis and we've managed to know the type of reaction we are going to have. Let us look at example number 2. In this one, we can see the substrate, we can see the nucleophile, we can see the solvent. So let us look at the analysis. Looking at the substrate, we can see that the substrate is primary. Looking at this group, it is attached to this carbon, which is attached to only one other carbon. So you can say this is primary. Looking at the nucleophile, we know that this will result into sodium ion and hydroxide ion. So you can see that this is a strong nucleophile. So we have a strong nucleophile, which is OH minus. And then we look at the solvent acetone. It's a polar aprotic solvent. In this case, you can see that we can fill in our table. Here we have acetone, which favors SN2 reaction. Now we can analyze. We have a primary. Our group is attached to the primary carbocation ion. We have a strong nucleophile. We have a polar aprotic. But the problem is, look at the leaving group. Our leaving group, it's NH2 minus, which is a very extremely bad leaving group. We are done with analysis. Now let us decide. We have a primary, we have a strong nucleophile, we have a polar aprotic solvent, but we have a weak leaving group. In this case, we are not going to have any SN1 or SN2, though the first three properties, they favor SN2, but you should know that since we have a bad leaving group which will not leave the substrate, we have no reaction. Let us look at this one. We analyze. The first thing we analyze the substrate. You can see that we have a primary substrate. The second thing that we have to check is the nature of the nucleophile. We know that this will be sodium and CH3O minus, which is a very good nucleophile. We can write it like this, CH3. Then we look at the type of a solvent that we have. We have a polar aprotic. Let us go to the table. One of the polar aprotic is CH3CN. So our solvent, we have a polar aprotic solvent, which is CH3CN. Then lastly, we have a good leaving group, which is a good living group. Then with this analysis we can decide whether we have a SN2 or SN1. For primary, we know that it favors SN2. For strong nucleophile, it favors SN2. For polar aprotic, it favors SN2. This can favor SN1 or SN2, but you can see that most of the properties, they favor SN2. So this will be SN2 nucleophilic substitution reaction. Now let us look at this one. We can see the substrate. We analyze now. The substrate, it has a primary. We look at the nucleophile. We know that this will be Na. So you can see that we have a strong nucleophile. We look at the solvent, we have a polar protic. Remember from the list, we said this is a polar protic. And then we look at the living group. It's a good living group. It's a good living group. Now we decide. For primary, we know very well that this is SN2. For strong nucleophile, we know that this is SN2. For the solvent, we know that polar protic is SN1. And then we know that for the good living group can be SN1 or SN2. So you can see that the most properties that we have, remember that we said this is not major, but it might assure us which reaction we have. So in this case, because of this, this will be SN2. Because we have SN2, SN2, we also have SN2 here. So we conclude that this will be SN2 nucleophilic substitution reaction. Let us analyze and conclude the type of reaction this will be. So we have a methyl halide. Looking at the substrate, we have a methyl halide. The second thing that we should check is the nucleophile, which is OH. You can see that we have a strong nucleophile, which is OH minus. We look at the solvent. It's polar protic, because you can see that it's H2O, it's water. Looking at the living group, which is Br, it's a good living group. Then from here we can decide. Our analysis for methyl, it favors SN2. Strong nucleophile, it favors SN2. Polar protic, it's under SN1. Then this can be SN1 or SN2. Like the previous example, we have 1, 2, 3. So it's 3 against 2. Then we can say this is SN2 nucleophilic substitution reaction. Now that's the last example. With these steps of analysis, you can actually tell any reaction whether it is SN2 or SN1. So under this you can put water, and you should know that this is an alcohol. So we have alcohols and water, which are acidic hydrogens. They have acidic hydrogens. In the next lesson video, we'll be looking at more examples. We might be looking at about 15 to 20 questions using the very same analysis for practice purposes. That's it for this lesson video. This is Wahula SJ. Thank you very much.